Hello everyone, my name is Wonsik, and today we'll be discussing image condition 3D scene editing. Before we begin, I'd like to say thank you to our teammates, Jessica, Brendan, and Aradhya, for their contributions. Let's get started. Look at this face on the table. We want to edit it into this face. To edit this 3D scene, we will use a diffusion model to get the edited images and fine-tune the 3D scene with them. Let's take its 2D slices, feed them into a diffusion model, get the edits, and that doesn't look right. The table also turned blue, and the color and pattern of the vase are not what we wanted. To address this issue, we propose a new 3D editing method leveraging diffusion personalization.
To quickly frame our work, we'll mention that 3D Gaussian splats are a novel method of 3D scene representation that allow for compact storage and high levels of detail, and methods have recently allowed for consistent text-driven edits to these scenes, but they don't allow you to introduce a custom subject in the same way that Wonsik has proposed, which leads to degraded quality and differences in detail from the desired result.
Our approach replaces the text-based editing pipeline in Gauss control with image-based editing in our custom edit model with various benefits of our approach. For training, we use a NERF dataset for multi-view images to create 3D Gaussian splats, and the DreamBoost dataset to fine-tune the diffusion model for specific objects. NERF provides extensive 3D modeling data, while DreamBoost focuses on object personalization. We resized and normalized the images to enable precise image-based edits, surpassing text prompt limitations.
Now let's talk about our methods. We use Gauss control and custom edit ideas for our implementation. Gauss control is a method for editing 3D Gaussian splats using a 2D diffusion model. First, it renders 2D views from that 3D Gaussian, and then it converts them using a control net model to the edited images, and then finally uses those edited views to fine-tune the new 3D Gaussian using pre-existing techniques. Our approach replaces the default control net with a special custom edit diffusion model.
Custom edit achieves precise edits by injecting custom cross-attention maps into the UNet module. Let's zoom in on one such cross-attention map.
Note the bear to the left. Now let's look at the cross-attention map for the bear token. Note how the cross-attention map highlights the bear section of the image. Now let's look at the cross-attention map for the bird token. We can see that the cross-attention map highlights the bird section of the image. So, by replacing cross-attention maps of specific tokens and passing them into UNet, we can achieve edits with high precision while preserving faithfulness to the original image.
Now let us introduce our custom Gaussian method. Here's how the editing pipeline works. First, we render images from 3D scene and edit them using a pre-fine-tuned diffusion model, and then edit the 3D scene based on these edited images. To start, we fine-tune the diffusion model using the reference image we want to edit. This process is called personalization. Next, we extract 40 images from the various angles of the 3D scene. Then, these images are edited using the fine-tuned diffusion model using custom diffusion. Finally, the 3D Gaussian splitting model is updated based on the generated images, resulting in the fully edited 3D scene. And here's the result. Within the baseline model, we observed that when editing the vase, the color of the table changes as well. Additionally, the vase's color also differs from the reference image. However, our method successfully edits the 3D scene while preserving the table's appearance, accurately reflecting the color and pattern of the reference vase. The following metrics are used for evaluation. VQA score leverages the capabilities of advanced VQA models to assess how well the scene has been edited. Clip similarity score uses clip cosine similarity between clip embeddings to evaluate the images. Additionally, factors such as consistency of the 3D scene and its realism compared to real images are also considered the evaluation.
Human discernment should be used when looking at quantitative scores from those of VQA score. The prompt on the left is, does this figure show an image of a cat? Our VQA score benchmarks would imply that our edited image looks the most like a cat, and therefore we have a good edit. However, if we reframe the benchmarks, so is the figure on the left the same as the figure on the right, given that both depict image of a cat, this would now imply that our original image looks more like our reference image than our edited. If we yet reframe our prompt again, we get yet a different conclusion. So our actual conclusion should be that user satisfaction cannot be quantified, and we should always verify our quantitative scores with qualitative judgment.
Our results show that our custom diffusion model surpasses Gauss control in consistency and visual accuracy across views. Higher VQA scores and user confirm shows better alignment with reference descriptions, especially for complex features. This demonstrates the effectiveness of image-conditioned editing in enhancing precision and consistency, paving the way for improved 3D editing workflows in real-world applications.